the roller coaster problem. If you can understand a roller coaster problem, you're going a long way to looking at conservation of energy. Roller coasters, in their first incarnation, I think it was maybe in Atlantic City, New Jersey, places like that, where people were sliding, riding canvas sacks down polished aluminum sections of track. That was kind of the first use of height to velocity transfer, so conservation of energy, in an amusement park setting. The higher up you were, the faster you travel down the bottom, you let gravity do the work. But you did work first to put yourself up there, but you're not thinking about that on the way up. When you look at a roller coaster, it is absolutely a construction designed to transfer from height to velocity and velocity back to height. And one of the problems that is asked of you on the workbook pages is they have a 1 kilogram ball at the top of a 2 meter tall hill. It rolls down the valley, up to the top of a 1.5 meter hill, down another valley, and finishes up at the top of a 1 meter tall hill. Doesn't finish there, but it's still traveling at that point. And they say, how fast is it moving at the top of the 1 meter hill? Okay. Important thing to keep in mind here. You don't need to look at what's happening here. We don't care what's happening there. We know with the conservation of energy that if we have potential energy here and kinetic energy here, or however what we have here, okay, that has to carry through to every single point we look at, whether it's here or there. We're going to keep that same number because there's no friction present. So if we look at this, I want to I call it independence of path, in terms of it doesn't matter what happens in between, it's the endpoints. That's all that matters, because we're assuming there's no friction. And it sounds weird, but it doesn't matter what the slope of this track is. If it goes from here to here, if I drew the track and I said it's doing this, if I said it goes down a massive amount and comes back up, if you wanted to go through the math would prove that, yeah, it moves at different rates in here, but we get back to the same velocity over here, because this one, it's going to pick up a ton of speed, and it's going to start to lose it on the way back up. This one is going to be slow and steady, not going to be moving as fast, but it's going to be just kind of a slow and steady increase. We're going to hit the same velocity over there every single time. Now, this guy might outpace this one. We don't know who gets there first, but conservation of energy will tell us that it doesn't matter what happens in between. It's like what happens there. So if you look at the values here, the potential energy, if I kind of lay this up here, we have M, G, H. Now it's not moving initially, so this is my KE. That has to equal, now I'm going to go all the way over here because, like I said, this doesn't matter. You'll get the values here, but because the total over here has to equal the total over here, I'm going to look at what happens over here. We have 20 joules. So it's like this. We have 0 kinetic energy and 20 potential, if you want to think of it that way. When we get over here, we know that the potential energy, it's a 1 kilogram object, again, times 10 times 1 meter. So we have 10 joules of potential energy over here. And they want to know how fast it's going. Well, if you take a look at this, we had 20 in potential over here, all potential, nothing kinetic. Over here, we have half of that. Well, that should make sense, because guess what? We've lost half the height. So we should only have lost half of that value, which means guess what? If you started with 20 and you got 10 over here, the kinetic energy has to be 10 joules. And from there you can figure out the velocity and then work backwards. Technically what you're looking at looks like this. If I do KE plus PE equals KE plus PE. Well, the kinetic energy is 0, and you just calculated out, or we calculated out. We have 20 joules there. Well, the kinetic energy we don't know here, but I know it's going to be 1/2 times 1 times V final squared. And the potential here is 10. So you've moved 10 joules into kinetic energy. So we get 10 equals 1/2 1 V final squared. Okay, multiplied by 2, you got 20. There's no reason these are the same numbers. That's just the way the math works out. This is going to be V final. And you take the square root of that. And I believe this is going to come out to be 4.5 or 4.47 meters a second. Not squared, though. Okay. There's another subtle point I want you guys to see, because it's a little kind of a trickiness that happens here. If you look at the math, when you have no friction present and you only have kinetic and potential energy, a problem can be presented to you where there is no mass. So if I didn't tell you this and I said, I want you to kind of figure this out, and you're like, well, I can't figure, there's no mass. That's typically when I'll say, work the math. So the kinetic energy, watch this, 1/2 mv squared plus mgh. That's left-hand side kinetic and potential terms. Regardless if there's zero, I want to have the term in there. When it gets over here, it has kinetic energy again, so 1/2 mv final squared plus mgh. Now I don't know the mass, but look very carefully, guys, at what's happening. If you have a term that is present in every single equation, you can divide by that term and cancel that out. We have a mass in every single term. So it doesn't mean it's zero. It means that you can go through and say this. As long as whatever I do on the left-hand side of an equation, I do the right-hand side, it's valid. This means that you could do this out without the mass of the object, and you can get the correct answer. So keep that in mind, because I'm probably at some point going to throw that at you in some kind of an assessment to see if you're paying attention. Can you do it by substituting a mass in? Absolutely. But if you do this way, that's like a full credit, because you show me the fact that mass cancels. So keep that in mind only when potential and kinetic energy are involved. If you have energy lost over here, you can't do it, because there's not a mass term in there that you can tell immediately. So when you're doing these problems, always look to find the simplest way to solve. If you start working through these equations and you can see immediately that, hey, I only need these three terms, don't write the kinetic energy term if you know it's zero. I'm going to know what you mean if I don't see it there. So as you go through these, get used to setting them up. What's your MHV? What's your MHV? And start to solve that way. All right. I hope that kind of helps you out with at least looking at a roller coaster type problem. The independence of the path, like what happens in the middle, it's like being in Vegas. It doesn't matter, stays there, here and here. That's all you're looking at. That's all I care about. That's all the math is going to need to be done. And that if you see mass in every single term, you can cancel it out and you don't need to have it there. All right. So conservation of energy, roller coaster, no friction. Thanks, guys.